Hi, this is Mrs. Rodolfi, and I'm going to go through these two notes sheets, this graphic organizer and foldable on geometric. Make sure you have the materials, and let's get started. So the first one I'm going to do is the geometric sequences formula. So we've talked about arithmetic sequences in the past, and similar type of formula. This is in function notation. So we have f of x equals, and then a, in the past, I represented that as a sub 1 with the explicit formula, but this is another way to represent it. So a is the same as a sub 1 times r, which is our common ratio, to the x minus 1 power. So a would be the first term in the sequence. So this again is when we're dealing with sequences. And then your r is your common ratio. I'm going to add in sequence. And to find the common ratio, we would take the second term and divide the first term. So back when we did arithmetic sequences, that's when it was adding or subtracting. It had a common ratio each time, and we would take the second term minus the first term. So common ratio now is what is it multiplying by each time. So now we're going to do the opposite of multiply. We're going to divide. And then x would be the term number, or number of the term that you are trying to find. All right, now using this formula, we are going to practice doing some of these geometric sequences in this foldable. So I'm going to keep this formula handy. All right, so we want to write our rule, which is also known as the function notation in this case, or the explicit formula. So for the rule, we first need to find the first term in the sequence. So our first term is 1.5, so we would put f of x equals 1.5 times, now we need to find our common ratio. So I'm going to take my second term, divide my first term. You can pick any two consecutive terms in the sequence. So I could do 3 divided by 1.5. I could do 6 divided by 3, 12 divided by 6, and so on. And that would equal 2. So my common ratio for this sequence is 2. And then to the x minus 1 power. Now we need to use it to find the sixth term. So f of 6 equals 1.5 times 2 to the 6 minus 1 power. And then use your calculator. So first I would simplify the exponent 6 minus 1, so that's 2 to the 5th power. So 2, and then remember use this caret to the 5th. That is 32. Then I would multiply it by the 1.5. Oh, I forgot to put times 1.5. 32 times 1.5. And our answer is 48. So f of 6 equals 48. So this says the sixth term in the sequence is 48, or the sixth number in the sequence. For graphing it, I am skipping the 10th term. So the 10th term, f of 10, equals 1.5 times 2 to the 10 minus 1. All right, same thing, simplify the exponent first. 10 minus 1 is 9, so I would do 2 to the 9th power. 512 times 1.5, and our 10th term is 768. So f of 10 equals 768. Now for the graph, we don't need to number it. Let's just assume that each of these lines is 1 unit. So again, for sequences, we talked in the past, think about, would this be a continuous graph or a discrete graph? So think about that as we're plotting the points, and then we'll decide at the end. So the first term in the sequence is 1.5. So if I were to write the ordered pair for this, it would be 1 for the term number, and then the term is 1.5. So these values in your sequence are your y values, and then, this first one is 1.5, so 1 would be my x. The second term is 3, so 2 would be my x, and 3 would be my y, and so on. The third term is 6, so 3 would be my x, 6 would be my y, and then the fourth term is 12, so 4, 12. So let's just plot those, assuming that each line is 1 unit. So 1, 1.5, so I go right 1 and then up 1.5. 2, 3, 2, 1, 2, 3, 3, 6, and 4, 12. All right, so what did you decide? Should we connect our points or not? Continuous or discrete? If you said discrete, you are correct. Remember that in a sequence, we can't have half a term number or, a decimal or a fraction of a term number. It's, it's the first term, second, third, fourth. So we have to keep this discrete because our term number can't be decimals or fractions. The actual term itself can, but not. So to label, x would be our term number, and our y, which is, remember, y is the same as f of x, this would be our term. So you always want to think about what's on the x-axis. Can that be represented by decimals or fractions? In this case, no. Term number has to be whole numbers. Now our term on the y-axis, that can be decimals, like the first term was 1.5. So that's okay, but if the x-axis cannot be defined as decimals or fractions, then we keep it discrete. All right, going to the inside. All right, so our first step is to find the common ratio. Second term divided by first term. I'm going to just pick these first two terms. 16.2 divided by 18, 0.9. Remember, as long as it's a rational number, a terminating decimal, then you can write it as a decimal. If it is an irrational number or even a repeating decimal, keep it in fraction form, because then you're going to start rounding and you're not going to get the exact answer. So in this case, this is an exact decimal, 0.9, so we can use the decimal form of it. So just to show how I found the common ratio, I did 16.2 divided by 18 equals 0.9. Then we would write our rule, f of x equals, and then the first number is the first term, which is 18, times our common ratio, 0.9, to the x minus 1 power. All right, let's find the sixth term. So let's substitute x equals 6. Again, simplify your exponent first. 6 minus 1 is 5, so I would do 0.9 to the 5th power, and then multiply it by the first term, 18. And then for this one, we do have a decimal. So f of 6 equals 10.62882. 10th term, f of 10 equals 18 times 0.9 to the 10 minus 1 power. 10 minus 1 is 9, 0.9 to the 9th power times 18. So this does give us an irrational number, but in this case, we're just going to have to keep it that way. So just be mindful if on a quiz or test it says, round to the nearest hundredths. In this case, we will just write out the entire thing and do the ellipses at the end to show that it does continue forever. It's a non-terminating decimal, so f of 10 equals 6.973568802 ... All right, graphing it. Again, each of these lines is 1 unit, so let's label the term would be on the y. This is your f of x, or y-axis. And then we have the term number on our x-axis. So the first term is 18. So I would go up 18, so over right 1, and then 1, 2, 18. All right, the second term is 16.2. So if I know this was 18, 16 is right here, a little above it. The third term is 14.58, so 16, 15, so about right here. And then the fourth term is 13.122, so this was probably about here. All right, last example. Find the common ratio of this sequence. So again, pick any two consecutive numbers. I'm going to start with 20 and 15. Take the second number, divide the first number, 15 divided by 20. And we get 0.75. Or you could also use the fraction 3/4. Again, this is an exact decimal, so it's okay that we use it. All right, our rule f of x equals, first term in the sequence is 20 times our common ratio, 0.75 to the x minus 1 power. Sixth term, f of 6 equals 20 times 0.75 to the 6 minus 1. 6 minus 1 is 5. Then we do 0.75 to the 5th power times 20. And we're going to get another irrational number. So let's put f of 6 equals, actually this one isn't as many decimal places, so that is an exact decimal, so we'll just write it all out. 4.74609375. And our 10th term, f of 10, I don't know why I'm writing 6, f of 10 equals 20 times 0.75 to the 10 minus 1. And f of 10 equals, so 10 minus 1 is 9, 0.75 to the 9th power times 20, 1.501693726. And then for graphing this one, term and term number. All right, our first term was 20, which is at the very top. I know from the other one this was 18, so I know this will be 20 up here. And then they're counting by fives, 1, 2, 3, 4. These darker lines, so I know this one's 15, so this was 215. And then 311. Oh, it was 11.25, so a little above 11. And then 8.43, so a little below 8.5. So that's 10, that's 9, 8. So about halfway between. One other thing I want to point out with common ratios and with geometric sequences is notice the type of graph. So again, we keep them discrete, we don't connect the points, but what if we did connect the points with a line? Would this be a linear relationship? So kind of imagine a line being created. What shape would that be? It would kind of be a J shape, which we've talked about in the past. And if you remember, these all would represent an exponential function. So we will be getting into a lesson on exponential functions next week. But I just want to point out and get that word out there that these are exponential functions. They would form that J shape. As we increase this, notice how it kind of starts small, 1.53, then 6. Then it starts getting larger and larger at a faster rate. So it's exponentially increasing or decreasing. And so same with over here. This one kind of might look like a straight line, but as we plotted more points, it would have that curve to it. So they are all exponential functions as well.